Welcome to our video on the design and fabrication process for BioFlex, a rehabilitation device for patients with spinal muscular atrophy.
Hi, I'm Nina.
Hey, I'm Adua.
Hi, I'm Ashmita.
Hi, I'm Hannah.
Hi, I'm Samir.
Hey, I'm Sawyer.
Hello, I'm Krish.
Our client, Fernando, is an 11-year-old boy with type 2 spinal muscular atrophy. SMA is a debilitating neuromuscular disorder that causes muscle weakness. Fernando has weak arm mobility and strength and wanted an easily accessible and effective at-home workout device that would maintain and enhance muscular strength and physical health. With extensive research on type 2 spinal muscular atrophy, we decided to move forward with fabricating a weighted pulley design.
The device will attach to the back of the wheelchair through a well-designed system that accounts for the product's forward center of gravity. We'll use Arduino coding and sensor technology to move in both a rowing and pullback motion. For comfort and attachment, the device will have memory foam padding which will be placed on the inside of the product and attached by buckle straps that can tighten and secure the product to the client's arm while being safe and easy to remove.
Alright, so I was responsible for the overall build of the design, so let's get through it. So basically, when looking at the prototype, initially my only focus was the exoskeleton of the arm. So when we attached it to the arm, we knew that all functioning motion of the prototype was present, and it worked. Now, in building the second, third, fourth, fifth, and sixth iteration of the CAD before we went to the actual model, what I did was build in redundancy. So if you see, every single piece is modular, with only 2 screws needing to remove one panel, side, or portion of the device, which means you can quickly access, edit, and change different parts of it. Now, one of the other things that's cool is we also accounted for design manufacturing tolerance errors, meaning, say for example, our line of motion from the motor to the arm is off. There's flex shaft couplers in place that allow for the motion to be translated on a bent angle and then recentered once it reaches the points where it needs to go. Furthermore, everything is made with Allen key-based screws of sizes ranging of M4, M3, M2 in order for it to be universally standard and easily disassemblable.
For the attachment to the wheelchair, we initially wanted to make it so that it could support the weight of the gearbox and arm so that it wouldn't shift in any way during use. Our first design mimicked the functional support of the trapezius muscles, where bungee cords would stimulate muscle contractions to provide support to the system as a whole. However, due to the size and lack of functionality, we decided to shift our direction to a different design.
Our final design consists of a wooden base attachable to the back of the wheelchair that has slots where wooden blocks attached to the gearboxes could slide into. The blocks are held in place by an aluminum panel screwed into the base. In all, this design was effective in supporting the arm and attaching it to the wheelchair.
The electronics of our device consists of a few main components, first being the 2 stepper motors. These stepper motors are housed in the metal box and are responsible for the movements of the arm through a belt drive system. The stepper motors are powered and controlled by their own respective Arduino and LN298 motor drivers. These components interact with each other based on the client's own movements and abilities. This is done through the use of an EMG muscle sensor that detects the electromagnetic signal from the arm and relays that information through the Arduino and motor drivers to adjust the movement of the stepper motors, thus allowing the arm to move accordingly as well.
For this project, I worked mostly alongside with Hannah, attaching the prototype to our patient's arm and ensuring that it was comfortable. We first tried using a thermoplastic mold, but it didn't end up shaping to the arm and would melt unevenly. So we ended up switching to create a memory foam case that adjusts to our patient's arm using buckles.
First, we would like to acknowledge our client Fernando and his father for allowing us the opportunity to work on this project.
We would also like to thank Dr. Suarez for her unwavering support throughout this whole semester.
Furthermore, we'd like to thank our Fab Fellow, Ash.
Thank you for Mobile for providing us the wheelchair to test our device on.